And Samya Kargi. For our machine learning final project, we built a chest cancer detection system using deep learning techniques on CT scan images. So, lung cancer is a leading cause of cancer related deaths, but early diagnosis can dramatically improve survival chances. The problem that we encountered was interpreting CT images is time consuming and prone to human error. So what we did was build an automated classification system based on the efficient NetB0 architecture to speed up and support this diagnostic process. So our dataset comes from Kaggle and includes CT scan images labeled under four categories. They are adenocarcinoma, large cell carcinoma, squamous cell carcinoma, and normal normal class. So the images were already in JPG and PNG format on our dataset, so we didn't need to handle DICOM processing. And we split the data into 70% training, 10% validation, and 20% training sets. After redistributing our balance, we had 119 training images, 52 validation, and 64 testing. Uh, so, looking at the training breakdown, we had 76 adenocarcinoma and 32 large cell, 57 squamous cell, and 34 normal training images. So we resized all images to 224 into 224 and applied data augmentation. That included flips, rotations, color jitter, and affine transformation. It helped our model generalize better. We used efficient NetB0 as our backbone. It is a compact and high performing convolutional neural network. That's why we chose it. The model was pre trained and fine tuned with a custom head using a dropout layer of 0.3 and a linear output for 4 classes. We used the Atom optimizer with a learning rate of 0.0003, cross entropy loss, and a reduced LRO and plateau scheduler. And the training was done with early stopping set to 7 epochs of patients and a batch set of 16.
And yeah, now I'm going to take over from slide 6. Our model trained for a maximum of 30 epochs but stopped early at epoch 14 due to no further improvements. Each epoch's process was tracked with TQDM and validation was done at every epoch. This strategy helped us get the best performance without overfitting. And for the system architecture, we built a full stack development pipeline. The backend uses Fast API to serve the model via REST API and PyTorch for inference. The model is also stored on AWS S3 for scalability in the future, and the frontend was built using Next.js and Chakra UI to allow users to upload a CT scan and get a prediction in real time. And for MLOps, we used Git and data version control DVC for version control and dataset tracking. Then for the performance, our model reached a 96.15% validation accuracy and triggered early stopping after 14 epochs. On the test set of 315 samples, it achieved an overall accuracy of 93.75 percentile with 87.5 on adenocarcinoma, 90.91 on large scale, 100% on squamous cell carcinoma, and 100% on normal. We had zero false positives on the normal class and high recall across the board, which means our model really missed cancer cases. And now talking about the achievements, we are proud of what we accomplished because like we built a full ML pipeline from scratch. We also were able to deploy end-to-end cancer classifier. We also achieved nearly 94% text accuracy and incorporated best practices like augmentation, early stopping when we train the model, and dataset tracking with DVC. For the future improvements moving forward, we'd love to explore more advanced models like vision transformers or ensemble techniques. So we are also interested in handling multimodal learning, combining image data with other inputs like patient history, and we'd like to add explainability features like GradCam and better system monitoring for a real world development. Now we'd like to walk you through on what we built on real time. So this is our model that we built. So So we just, this is a feature, you can just see the front end, we can just drop and drag the images. So let's just go through some images. So if this is the images, let me just drop it down, just take the image and just drag and drop here with the drag and drop feature, and it tells me that this, the confidence is large cell carcinoma or large cell cancer. So let's see if it's true or not. Let's go inside the website, should be under this, and yeah, the image is here, and we can see that the image represents non-small cell lung cancer. So non-small means large, so large cell sarcoma, so we are correct in this one. So let's also explore other like normal chest CT scan images here. So let's just remove this and let's just see some normal ones. Let's just see, let's just go to this one and let's just drop this. So this is telling me normal, and we can also see if we go inside here, it is just telling us that this is a normal CT scan of a chest of a 9-year boy. So yeah, this is definitely a normal CT scan which has no any infections on it. Let's just try another one to see if this really works. So we'll go to this one and let me just do this once more, and let me just drag and drop. Now it's again telling me it's large cell sarcoma. So if we go to this photo and check, okay, so just a sec, which one? Yeah, it's a lung cancer. uh let's just try another one, just a sec. uh yeah, the it shows the 87.6% confidence on large cell lung cancer. So this should also, according to our model, they should also be large cell sarcoma. So we can also try with different images, but and in the end I want to tell that the main issue that we faced in this project was getting more CT scan images, because like all the we used all almost all the CT scan images that were publicly available on Kaggle. So we had more difficulty right now in this phase, because like we wanted to test if our model really worked or not, and we only found like few 3 or 4 images that were really valid and we could use to test our model. So and whatever the images that we found for testing, the model really worked for us. So we feel that our model has a great accuracy on predicting these 4 classes: adenocarcinoma, large cell sarcoma, squamous cell sarcoma, and normal. So this is the model that will bit, and now I'd like to end our project. Thank you.